So hello everybody, good afternoon. My name is Inga, as it was mentioned. I will be giving a talk entitled When A/B Testing Isn't an Option, an introduction to quasi-experimental methods. Perhaps before we jump into the topic, I will just say a few words about myself. Actually, I will repeat. I currently work as a data scientist at OLX in Berlin, but my background is in economics and econometrics. So I studied economics, and I started with that, basically. And I'm still, at heart, I'm an economist, and you will see in the talk why I mentioned this. So, without further ado, let us start. And I would like to start by calling a quote by Leo Breiman. So, in 2001, he published his very famous paper about two cultures in statistical modeling. So basically, Breiman said that there are two cultures in how statistical modeling is used to reach conclusions from the data. And one culture assumes that data is generated by some stochastic data model, while the other one is most focused on algorithmic models and treats data mechanisms as unknown. So that first culture is something that we would label as econometric statistics and econometrics these days, or at the days of Breiman. And this other culture is more something that we would label machine learning these days. So actually Breiman, he argued that 98% of statisticians and econometricians follow that first culture. This is not true anymore, because these two fields, they converge, and for example, in economics, AI methods they started to be incorporated into research. And also, in machine learning, there's some interest in causality and structural modeling. Also, the fact that we are having this talk today is an evidence for that. So, yet about those two cultures. So, what they are about? So, data modeling culture, theory-driven, and allows to identify quantities of interest, like, for example, treatment effects in causal relationships. On the other side, we have this algorithmic modeling culture, which is theory agnostic and purely data-driven. So what it focuses on is prediction. So if you follow that algorithmic modeling culture or machine learning approach, the main goal is to get the why right? So to have the proper prediction. And machine learning models, methods, they are said to work really well if they can make an accurate prediction on a holdout set. This is all you need, right? So you have a holdout set, you have still good accuracy of your prediction, and that is it. So this is the main focus. In contrast to this data modeling culture, when prediction is not everything, so we rather want to understand how things are modeled, what are the forces, and how each of those forces shapes the outcome variable, right? So more about the process. I said that in the machine learning, it's mostly predictive considerations are taken into account, while causality, equilibrium, or feedback effects are not. But one might argue that this is also changing, right? Because there's been so much interest in the recent years about model explainability, interpretability, these things are related with that first culture. Or, for example, there's discussion about bias and fairness. So are our machine learning models fair? But this is something that is discussed post-fact. So once you have your prediction, you can analyze, okay, is my model fair or not? It's not something that it's accounted for, optimized for on the go. On the contrary to this, let's say, statistics or econometrics way of doing. So, yeah. So causal inference, so typical application of this first, let's say, culture is causal inference, while for the other it's prediction problems. So let me motivate that distinction with some example. So in economics, and also like if you use common sense, when you think about prices and demand, you should come to a conclusion that when prices are increasing, then the sales or demand is decreasing, right? So the higher prices, the lower demand or the lower sales. That's like, that should be natural, right? But this is not something that is always observed in the data. So in the data, sometimes, so here is an example. In the scatter plot, you can see we have price and sales, which are positively correlated. So in this example, once price increases, sales also increases. This is a bit counterintuitive, but this is, yeah, it's in many data sets, actually. To like better picture it, or yeah, to visualize it, we can think about that example in terms of, for example, demand for hotel rooms and prices for hotel rooms. So when you're booking a hotel room, you're booking a hotel, right? You want to go on holidays, or I don't know, on a wedding, or to a conference, right? Actually, we are at a conference at the moment. So you see that, yeah, there's basically prices are high. So what's going on with availability? It turns out that hotels are full. So there's been a lot of sales. So prices are high, and sales has also been high, right? Which, yeah. So if you have such data, and then you try to approach this, let's say you want to understand the relationship between sales and price. So you could try to fit a regression model or any other model. And what most likely you would find out is that, yeah, price is positively correlated with sales, or if you increase the prices, sales will increase too. But yeah, it's, and so here you clearly see that fitted line is, it has a positive slope, right? But that model is wrong, and we know that, right, by economic theory and that common sense. So what is going on there? So what in fact happens is that we have this third force. So we have relationship here in this diagram between price and sales. So price definitely impacts sales. But we have this other force, demand here, which impacts both price and sales. So when there's an increase in demand, both price goes up and sales goes up. And it causes basically the relationship between price and sales to be distorted. So with the data we had, which we saw on that scatter plot, it would not, so we could not control in any way for that demand factor, which definitely impacted the picture. So in terms of some nomenclature, the demand in this case would be a confounding factor. Yeah, and then sales is our like outcome variable, which we wanted to understand or predict, and then price would be explanatory variables. And yeah, they are basically distorted. So you may ask, okay, so then how do I answer that problem? How do I understand, if I want to understand how actually price is related to sales, or if I want to like estimate demand for those hotels, what do I do? The answer is that you would need to basically change the price to generate a data set that would that could be used to understand the problem. You would need to change the price, but hold everything else fixed. So in the example which we saw before, like 2 slides ago, so there were some variation within price, but what we didn't see is that there were other factors that were changing as well. So here, in contrast, in the setup, we want to change only the price and keep everything else constant. And this is something else, and we didn't have that in the data. So how that problem could be approached, you may ask. So this is like widely known problem in economics, and economists has been looking into this for decades, if not more, right? Because it's like basic, demand model is the basic model, and you learn it in your like not even first semester, first perhaps month of your economics course. What economists would do, they would build so-called structural models. So these are models, like you might think about them like as a set of equations, functions, which explicitly model relationships in the data. So they could, for example, account for how people, our subjects in the experiment, right? How they make this, how they maximize their utility, for example, right? So they maximize their utility by, they have some preferences about how much they're going to pay for a given goods, like in this case, hotel prices, hotels, and this is something that you put explicitly in such a structural model. But they're not those models, like, okay, the model for demand is not that complex, but once you run into some more complex scenario, the model would also get way more, would get giant, right? So like solving such a model is not really easy sometimes. And also, before you build a model, you need to have a theory, right? Because you need to like represent the forces, which, you know, what's happening with a set of equations. So that theory, there might be some contradicting theories, for example. So how do you know which theory is right? It's sometimes difficult to say. So is there other solution, you may ask? And yes, there is other solution, so which seems perfect. So in order to estimate the demand curve, you could offer random prices to your clients, right? So you're a business, you can do that. You offer them random prices, so basically you run total, the price is totally independent of all confounding factors, right, including the demand. So once you collect enough data, you'll have a perfect estimate of the demand curve. That sounds amazing, but no, no. Because like, if you think about running such an experiment, like it would be incredibly costly. Like, such a business would go bankrupt in like soon, right? Because there's no like optimization of any sort of prices. So it's not really the ideal scenario, but in theory, could be done. In general, like experimentation is like gold standard for measuring the effect of an action, and so it's widely adopted and used. So let's have a look into that. So especially in business, there's some Silicon Valley label for randomized controlled trials, A/B testing, right? I assume like most of you or all heard about this. So these are so-called completely randomized designs. And it's an experimentation technique in which subjects are randomly assigned to control and treatment groups. So I highlighted here the word randomly because it's key. So the assignment should be really, the assignment of subjects who are treated should be really random. And if we have random assignments, we ensure that our treatment is not correlated with any third variables, which, basically both control and treatment groups, they are affected with the same confounding variables. So we can see the difference between a result of like our treatment. So in this so-called potential outcome framework, we define average treatment effect as in this, as here in the slide. So average treatment effect is expected outcome given that there was a treatment minus expected outcome given that there was no treatment. So just difference between these two expected values. But that being said, even though A/B testing is such a great tool, it's not always possible to run, to schedule and to launch an experiment or to design an experiment. So there may be for a number of factors that might not be possible. So the experiments can be costly, long-lasting, unethical, or illegal. I'm sure you could name more reasons like that. So to give some example, like you may think about the following problem, that you want to understand what is the effect of being fired, of somebody being fired on income of that person, on future income of that person, right? This is some question to which economists would be really interested. But yeah, how could you answer that question, right? How being fired impacts your overall income? So you may have that idea that you could design some experiments. So basically, in order to control for all the factors, you would have to assign subjects to the treatment randomly, which means that you would randomly nominate people for being fired or not. And being fired, it's a big thing. Like it has impact on, lives of those people who are affected. So this sounds unethical, right? So perhaps it's not the best idea to run this such an experiment. Also, there's another factor. So such an experiment would be long-lasting, because in order to truly understand what's impact on somebody's impact, like maybe lifetime income or expected income, you would need to run it for years, right? So there are like multiple problems arising already, right? So sometimes it's not possible. There's also like another scenario in which underlying assumptions for identification cannot be met. So something I talked about before, like randomization, right? So randomization, like random assignments of subjects to treatments, is really crucial. And like a scenario in which it's easy to, or which is perceived like, let's say, almost perfect for possibility of randomization is like if you have a website and you want to test some change on the website, right? So it seems like almost perfect because you can have like large number of subjects which are treated or not, and yeah, you can monitor them and so on and so on. However, even in that setup, there might be some potential problems. So, for example, you might not be, it might not be possible to totally separate users, or not separate, to actually identify a user that's using more than one channel, right? So you might have users that use some app and desktop version of your site, and that will bring some distortions, right? So yeah, so basically the same person might land in two groups, in control and treatment. So now, depending on the size of that issue, you may have biased results of your A/B testing, right? Another problem which could arise is dependency between treated subjects. So this is also something that should be avoided, and it is assumed that treatment which is imposed on the treated group does not impact the control at all. And yeah, so there should be basically no dependency between the groups. So, given those problems with A/B testing and experimentation at all, so now's the question: is there any other way, or can we approach the problem some other way? And the answer is yes. Some problems you can. So here we are at we have those quasi-experimental setups, or some call them near experimental setups or frameworks. So basically, those quasi-experiments, they are used to inspect past events, that's important, that resemble laboratory experiments. And they allow to discover treatment effects when randomized effects were not possible, for any reasons mentioned before, for example. Something important to know is that those quasi-experimental frameworks, in order to discover treatment effects, they require some small set of extra assumptions. And the assumptions will depend on the framework. We will go through a few of them, so you will see. So yeah, but each one of them has some extra assumptions that has to be made. And also important term about an identification strategy. So how you approach a problem and what assumptions you should impose, or what you should assume, is called identification strategy. And this is something to think about, when you have the problem, let's say, or the data, you should think, okay, given the problem, what should be my identification strategy? How the treatment was distributed, or this near experiment, this past event, how it happened, what should I follow? So yes, the first framework, the first quasi-experimental framework I would like to talk about, it is difference in difference framework. It is also known as, sometimes it's referred to as parallel trends design. So what's the idea here? So you need to have two groups, still, like in regular A/B testing, you need to have two groups of your subjects, control and treatment group. And it is important that the subjects are both control and treatment group, they are observed before and after the treatment. So this is key. Here in this example, you can see that we had a treatment on November 1st. So everything that is before November, that will be our pre-treatment period. And then everything on the right, that line, it is post-treatment period. And also we observe two groups, which in this chart, they're separated. So the orange one is control, and the blue one is, the orange one is treatment, and the blue one is control, right? So here's something happened. So as you may see from or think about from the name, there's this parallel trends term. What it means? It means that we need to, so just coming to assumptions, identification strategy. So it means that the crucial assumption in this framework is that before the treatment, we expect that treatment and control, they behave in some similar way. And in the similar way, here it means that they share the same trend. So whenever one is, let's say, growing, the other one should also grow. Whenever one is declining, the other one should decline too. So they should really share the same trend, or even it's referred like they should be like moving in parallel, right? And here I fitted regression lines. So you can see, I think, with just an eye, that in the pre-treatment period, those both groups, they share really parallel trend. And then another assumption which we make here is that now about the post-treatment period, is that, okay, if we identified two groups which share trend before the treatment period, we assume that they will also share the trend after the period. Of course, for the treated group, assuming that the treatment would not have happened. So if there is no treatment, we would expect both groups to still share the same trend after the treatment date. So this is like key assumption. What is also important to mention, because here in this picture, like it seems that the treatment is not supposed to affect the control group, but it seems that for the control group, nothing really changed in terms of the trend in the post-treatment, right? So this looks like single-fitted regression line, but it's not necessarily. Let's imagine that it's a bit different. So actually, that here the line started to like move downwards, right? So this could happen. It's not necessarily. It would not necessarily be like effect of a treatment, but there could have been some other third factors, like confounding variables, for example, right? Which, like this demand, which we saw before, that would change the picture, basically. And so in that case, we assume that, okay, our behavior of control changed, but we also assume that in this hypothetical scenario, that if treatment didn't happen, then the treatment group would also change the slope, because they share parallel trend, right? So disclaimer. I think I haven't mentioned that one important property is that even though they must share the trend, they might be on different levels. So level is not a problem; they just need to move in the same direction. So here in this chart, I put basically this violet line. It's what hypothetically what value of treatment group would be if it was not treated, right? So it shares basically the same trend as control, and it's like it would be one line. So now identification of treatment effects, it's basically graphically it's this difference, right? So what was observed minus what would be observed if treatment did not happen. So now you may think like, how is this solved? How to like you want to use that, and how can you solve it? So the Diff Regression is given by like this term, which you see in the slides right now. So so expected value of a subject is equal to alpha, which denotes level of the control group. Then beta d, which is the difference in the levels between treated and control group. and then beta t, which handles the trend. And then the most interesting one is interaction between the fact of being in the treatment group and the fact of being in the treatment period, in the post-treatment period or not. And really what we are interested in is that gamma coefficient. So this is our effect. This is our causal effect and interaction term. So I put some example. So we can see how this looks like in real life. Or actually, it's not real life because that example it's generated with some random process and assumptions and some noise. So so here just visualization of how you prepare the data to estimate such a model. So we have this T and D variable. So T is whether it's post-treatment or pre-treatment or post-treatment period, and D denotes if a unit was treated or not in general. And here you can see like some estimate, like output. So we have intercept, which is equal to 6.4. And yes, you can just look at the picture. So this is level of the control group. So yeah, looks correct. And I mean, it is correct because I know how I generated data. But also we have intercept for DT in our treatment effect. So 1.61 is our gamma coefficient, which we want to look into. Now, another quasi-experimental design, it's synthetic control. It was like, there was some buzz about it, about that method. It was even by Susanathy and Guido Imbens in one of their papers. It was mentioned that it's like the most important development in program evaluation in the last decade. So that's huge, right? To say something like that. So the idea is quite simple, however beautiful. And I like to think about this as some kind of generalization of difference in differences framework. So basically in difference in differences, we had just one group, one control group that was supposed to resemble our treated units, our treated group. Here the idea is that, okay, maybe we don't have to use just one control. Maybe we can have more control and somehow combine them in a way that they, in a better way, resemble our treatment group, right? So we don't have to limit ourselves to just one control. So synthetic control, what it requires, it involves construction of a weighted combination of groups used in control. So in other words, we want to create some forged control group from the controls which we have, and we want to create it in such a way that it will resemble our treated group as much as possible in the pre-treatment period, right? So basically any weighted combination of the controls you have built in such a way that it will resemble the treated group in the pre-treatment period. So there's obviously, so the method or the idea is beautiful, but there's obviously like a question like how do I build that synthetic control? Like what's the approach? Like there are some like in the most basic setup, you just may try to like run some, let's say, you may try to regress basically your controls on the treatment group, and then see if it works. You can use some regularization if needed. But yeah, there are some other techniques, but this is like out of the scope of the talk of this talk. So here is like I show basically my treatment group and then my created control group. So you can see that in the pre-treatment, my treatment and control, they are almost identical. So actually, it's too good to be true. This is due to how I created the data. In real life, that rarely happens. It rarely happens because, if you have perfect fit, right? So you would just assume that you have overfitting problem, and then you will have your synthetic control in the post-treatment periods would not be really reliable, right? One thing also about this post-treatment effect, so the average treatment, the treatment effects are basically the difference between synthetic control and treatment. So this is how you estimate the treatment effect in that setup. In this case, like the effect is really close to zero. So, yeah, also not perfect example. One more framework which I wanted to discuss is regression discontinuity. So, in this framework, the treatment is being decided based on some threshold. So. Here I use example from a book from Mahtari's book, Business Data Science, and we have an example of a design where where basically units with value of some feature which was above zero were in one group, and then. Basically units which had a lower value of that feature were in the other group, right? So there are some assumptions being made around that setup, and that is basically about that individuals near the threshold, regardless of their position, they are considered equivalent. So basically, so here we have the data. So we assume that individuals like around here and here, they are very similar, right? And that basically they share the same features. And that's I didn't say that feature, that variable which dictates the treatment is called running variable. We also have this continuity assumption. So basically, it means that if we change this threshold a bit, then individuals switching the group would behave similarly to their new group, right? So it's an assumption about the fact that really treatment affects the behavior. And the estimated effects. So in order to estimate effects, you basically need to take a difference around difference between groups around the threshold, right? And there are some methods to do that, but it's outside of the scope. And the estimated effects are basically the local average treatment effects, so they're only local. This is important. They should not be extrapolated to other values of the threshold. So it's the end of the talk. I just wanted to, I hope I gave you some overview of the quasi-experimental methods. I just would like to, as a summary, say that, what I wanted to tell to you is that remember that prediction and causality are not necessarily the same, and this cliche saying that correlation does not imply causation is actually, it's actually important, and remember to consider that. Thank you.
Thank you so much, Inga, for shedding some light on what we data scientists can do when we don't have the opportunity to do A/B testing. So we received a couple of questions, and I'm starting with the first one. So are quasi-experiments the same as so-called natural experiments?
Not necessarily. So natural experiments, of course, when there's a natural experiment, it might be analyzed with one of the quasi-experimental frameworks. So, for example, for synthetic control, I can give some quick example, right? There is this. Actually, we were in Berlin, but there was this case about Germany being unified, right? So one could ask a question like, okay, what GDP of West Germany would be if not the unification, right? And this is some kind of a question which you can analyze with synthetic control, for example. Actually, this is the example that synthetic control was introduced with. So, yeah.
Thank you a lot for clarifying this. So the next one, how do you decide whether diff and diff or synthetic control group is more suitable for a given task?
So with diff and diff, it's simple because you need to have parallel trends. So if you do not have parallel trends between your control and treatment, you should not use diff and diff estimator. As simple as that. So you need to check for assumptions, basically. And for synthetic control, it's all about building such a weighted combination of controls that will depict well-treated group in the pre-treatment period. So you can validate that.
Okay, thank you. And a little bit adding to this, if diff and diff regression assumes that the post-treatment trend has to be parallel, how would one handle possible long-term effects of the treatment?
Perhaps, maybe this diff and diff should not be used for long-term, for real long-term effects. It's more like local estimation, I would say. But I'm not sure. Maybe if that person that asked wants to clarify, or not sure.
Yes, and the second one, I think it goes in a very similar direction, and I think you already answered it. So diff and diff regression, we assume the relationship is linear.
It's linear, yeah, the trends are, yes.
So we assume that the trends are linear.
Yes.
And I'm not sure if this was the intent of the question, but in theory, could one also model, I don't know, like quadratic
So actually, like when you think about how data looks like, right? So you may see some, like, for example, seasonality. It can handle seasonality, but so if you have like seasonal data, like for example, weekly trends, right? So you analyze some feature which has weekly trend, which, like, if you look at, if you like plot that variable, then perhaps it will not be like linear as a single line, but yeah, as long as the two series are moving in the same direction, it can handle that.
Okay, thank you so much. Yeah, maybe one last question. So is there some way to mimic the A/B testing if there are no events in the past resembling the treatment? Oh, tricky one.
Sorry, could you repeat the question?
Yes, let's assume you want to A/B test something, but you don't have any data from the past that could actually resemble the treatment.
So, like, I'm not sure then how do I run A/B test if I don't have,
Yeah,
like, I don't know, how can I analyze something if I don't have data? Yeah.
Okay.
Sure.
Thank you a lot. Time is up. I have one quick announcement. So please, if you signed up for the evening social activity, don't get a badge like right before the event, then it will be very cute and crowded, but try to get it sometime now, maybe in half an hour or so. So there won't be such a long queue. Yeah, with that, thanks a lot, Inga, for shedding a light on A/B testing.